Hello, everyone. How's everyone doing? Perfect. So today, let's welcome Dr. Cliff, who will be talking about a very interesting topic: program your own computer in Python. So let's give it up for Cliff.
Hey everybody, Hack PyCon. So today I'm going to talk to you about programming your computer in Python. I'll be touching on some tools that you can use to do this today, but I'd also like to convince you that this is a worthwhile thing to do. The central thing I want to convince you of today is that your personal computer, the one in your hands or attached to the keyboard you are physically touching with your human fingers, is a super powerful machine, both in terms of raw computational power and in terms of functionality provided by the operating system. And you might not be taking full advantage of it. You can take control of your computer and do all kinds of cool stuff in Python. In yesterday's keynote, Corey told us about all the terrible stuff that's happening because we've ceded control of our computing to malignant forces. And changing political policy so that we can break those oppressive digital locks is indeed important. But before we go to join the revolution and live in a bunker, as a first step in that direction, maybe we could at least learn how to write an app, use the tools that already exist at our fingertips that the operating systems do actually allow us to use, which we seem to be mostly ignoring. You probably already do this at least a little bit, but we'll start out with a quick reminder that you can leverage your computer's power by running any code that you might normally run as part of a web app or a batch process or in a cloud-based CI system like GitHub Actions on your computer. Second, you can use Python to directly control the desktop apps that you already use. You don't need to parse their files or write little command line scripts. You can just manipulate them directly. Third, you can also write GUI applications, maybe even just really small ones, probably a lot less work than you might think, that can allow you to do things that just a web app or a command line script couldn't necessarily do. You probably already know that Python can do most of this stuff, but it's also probably seemed pretty daunting. There are new, unfamiliar libraries to learn. There are fewer examples to draw on. The main thing I want to show you here is that it's not necessarily that hard, and that in particular, it might require less code than you might think. The main way that I want to do this is to show you a lot of short samples of code. The samples are mostly complete programs that can be run as is. In a few cases, I'll have to show just one function or method, but all the examples are real code I've actually tested, no fake, and then some more stuff happens and draw the rest of the owl. It all runs. However, the point of getting the code to fit on one slide is not to actually let you read and internalize the whole thing. The point is to allow you to see the relatively small scale of the code examples and possibly read a few emphasized chunks. So to conclude the introduction here, I would be remiss if I didn't mention the inspiration I've taken from Al Swiegert's excellent book, Automate the Boring Stuff with Python. The ideas he describes there are related to the things I'm going to be talking about today. However, this is not a rehash of that material. Automate the Boring Stuff talks about a few basic things just to make programming interesting enough for it to be worthwhile for a beginner. Today, I'm going to be assuming you're already probably pretty good at Python. If you're at PyCon and you don't know what Python is yet, that'd be kind of a weird choice. So I'm just going to give you some ideas for doing cool stuff that you may not have previously considered. But let's start with the basics first. Your computer's pretty fast. We often treat our computers a bit like dumb terminals and leave all the heavy lifting up to cloud services. This is particularly true because Python programmers are back-end programmers. But why would I make that assumption? It's certainly not true for everyone, but a pretty strong majority of Python programmers are back-end folks. If we look at the JetBrains Python Developer Survey from 2022, using Python to write code for web applications and data science, extremely popular. Python sees a wide diversity of uses, but these are far and away the most popular categories. 43% of Python programmers do data analysis, 43% do web development, and 39% do machine learning. And if you're here at PyCon, you're almost certainly doing some of those things. That code tends to run on big, back-end cloud computers. While there are desktop applications in Python, it's far less popular for that. In the same survey, under 20% of respondents do desktop development. And front-end web development is so unpopular, it doesn't even show up on the survey. Although hopefully, given all the PyScript mentions in the talks this year, we'll see that change. But I suspect that even this small number is somewhat inflated by dilettantes like myself who just do a little bit of desktop programming here and there. 19% of developers means that nearly 1 in 5 is a desktop developer, but looking at the schedule for this conference, I don't think it's quite that many. Much larger conferences have between 1% and 0% talks about desktop topics. So, revisiting those numbers for the 2023 survey, we can actually see that the total has dropped to 14%, with only 5% now treating it as a primary activity. So not only do very few Pythonistas participate in desktop app development, but the number is dropping, which is the wrong direction. Despite the fact that we're writing back-end code, we are typically sitting in front of a desktop or laptop computer for 6 to 10 hours a day. We're certainly using our share of back-end code. GitHub is a cloud app with a pretty substantial back-end. And within a rounding error, 100% of us are on there. And yet, when we look at the data of what we use to write all that code, the programs we are spending our days typing into, the data shows we choose desktop IDEs and editors so overwhelmingly that cloud IDEs, like Amazon's Cloud9, are buried somewhere in the 2% other category. So clearly, we can see the power of our own machines when we want to get work done. So here I have some additional data that might be a quick, easy win for your local machine that doesn't involve learning any new tools or doing anything that resembles desktop development. Just a quick reminder that your computer is often surprisingly powerful. For good reasons, there's been a gradual move to run more and more of our test suites in the cloud, to do only small little partial runs locally, to test out just the specific thing that we're working on. Maybe even when we're running it locally, to run it like in a Docker container so that we're isolating it and keeping it in a small 2-core virtual machine instead of just running on your desktop. I'm sure that almost all of you run some tests locally, but the knowledge that you can spin up a bunch of jobs at once on the infinitely large parallel cloud can sometimes lead to a false sense of performance, always waiting to push something until you run your full test suite. Just for one trivial example, in the run-up to my original presentation of this talk 2 years ago, I tried running the full test suite for the Twisted project. Not counting the latency from pushing a PR to actually starting the tests, one Cloud Runner for our full test suite on the current version of Python for macOS took 125 seconds. My laptop at that time ran the full suite in 37 seconds. If I need the feedback from the full test suite when making a contribution to Twisted, not even counting the time that it takes to push the code and have all the back-end stuff kick off, I can get that feedback 70% faster if I just run it locally. My laptop, which admittedly was a pretty nice laptop for the time, can run the full test suite 3 times faster. I could buy faster machines on GitHub, of course, or I could do a bunch of work to chunk up the test suite into smaller runs to run it in a whole bunch more parallel resources, but why bother when my laptop is already this fast? Just to see how things have been progressing in the local versus cloud compute space, I measured again. I figured maybe the point I was making in this talk would have decayed a little bit in the intervening years. The Twisted project has added a bunch of new tests and new features in the meanwhile, but I've also gotten a new laptop. And as a result, the cloud has gotten a bit slower, and my laptop has gotten a bit faster. And now it's an 80% latency reduction. Local computers are so fast. You don't have to worry about resource contention with other users. If you're doing open source, you probably have to fit into the free tier on GitHub, even if you do have more resources than that, because it just wouldn't make sense to be running things that your downstream users would not be able to replicate and use. It's also amazing how capable a server a development desktop machine can be. To demonstrate this, I did a very silly benchmark. I ran Twisted just for a little bit of realism. I did give it a real HTTPS certificate, and the HTTP perf benchmarking tool for 50,000 requests just to get a quick baseline. I should stress, this is a test on my laptop, lots of other software running on a single core, with the benchmark running on the same machine. I set this up in like 5 seconds. And in 2023, the test server could process well north of 6,000 requests per second. Now, there's no database involved here. It's not like a realistic application. But I was developing web servers 20 years ago, and this is a wild number. Like, if you have 1,000 people clicking 6 times a second each, that's 1,000 concurrent users using barely 5% of the resources on a single core of the resources available to this computer intended for one person. Once again, I wanted to see, maybe single core performance has gotten worse, with newer machines because they're more focused on multi-core, but nope. We ran the test in preparing for delivering this version of the talk just to see if the newer hardware had maybe produced any gains. And again, the performance of newer hardware is even more impressive. Over 10K requests per second with a pure Python web server. This isn't even necessarily just a demo for your local network. If you have a small site that just needs to serve a few people, you can really put it on the web without bothering to maintain a server. ngrok.com has a free tier. You can point it at your machine, skip all the Docker, Kubernetes, Terraform headaches, and just run a program. Now, the eagle-eyed among you may have noticed that I put some asterisks on the previous slides. I feel like it's important to mention the caveats here. There are lots of good reasons other than performance to put your app on a server. You won't be able to get a single self-hosted computer to be reliable enough to do mission-critical 24/7 tasks on, and just for security reasons, you wouldn't want your public CI server to be your laptop. What I'm pointing out here is that if we move to the cloud for reasons like availability, security, and repeatability, we don't lose track of the value of also having usable local development environments. It's unfortunately common for local development environments to just decay as teams scale up and depend more and more on shared resources. So this is just a little gentle reminder not to do that. That's also why I didn't want to spend too long on this section of the talk or do a bunch of really intense benchmarks here to prove how great it is. Mostly what I want to talk about are tools for leveraging the unique capabilities of local computation, but it's worth remembering that even just in terms of like computation, your local machine is surprisingly fast, much faster than you need for a lot of things, and under zero contention from other users who need to do something at the same time. Okay, so now on to something a little bit more fun. Rather than just getting a bit of a speed boost, let's talk about new kinds of functionality. So to make this a little bit more interesting, rather than a few vague hypotheticals, let's tell a story. Imagine for a moment that you are a C-list micro-celebrity in the Python community who has to give a talk at a Python conference. You're trying to decide what tools to use for your talk. You're also nearly a caricature of middle-aged ADHD, so you're massively overcommitted and you have a limited amount of time to work on the talk. This is a bit of a digression, but it might be useful for those of you who also need to give technical talks. Getting the timing of your talk right is important. You don't want to be rushed at the end, but you also don't want to end too early. So if you have to give a long talk, there are two ways to get the right length for it. The most common way is you write some slides, you practice delivering it, and then you see how long it takes, add material if it's too short, cut for time if it's too long. This requires that you go through the full length of the talk every time you get the timing wrong. This can be pretty time consuming. The pro move is to write it all out as a speech. Do a word count to get a quick rough estimate for how long the talk is going to be, then iterate on it until it's pretty close to the length that you want. It's been long enough without a slide with code on it though, so here as a treat, let's have a little Python function just to take a word count, print out some time estimates that might be useful in this context, just a little bit of simple math on a word count, and some average words per minute speaking speeds. This slide is also a rhetorical device because the whole point is that it's not calling any interesting native computation local APIs. It's just regular Python that's easy to read because we all know Python. The output of it looks kind of like this. But here we run into a bit of a problem. For this talk that you're preparing, you're familiar with two different presentation frameworks. One, Reveal.js, lets you write your talk in plain HTML. It's handy for technical talks that have a lot of code in them, since you can include external files and version control and Git and stuff. And with HTML5lib, it's super easy to reach into the talk and grab the presenter notes for word count. You've even made a few presentations with it before, so if you're familiar enough with it to be productive, you've even presented a Reveal.js presentation at the very same conference where you're giving this talk. But the talk you need to prepare is now 50 minutes long. You got a lot to say. Setting up a whole new Reveal.js project can be an annoyingly large amount of work. You don't want to do that on a deadline. In this absolutely illegible slide, we can see the head tag, not even all the preamble and configuration that comes after that. So a faster tool for actually writing the talk would be Keynote. It's a GUI, so it's quicker to lay out the slides, easier to work with the images and stuff, take screenshots like this one. Given the tighter timeline, you want to use that, so cool, let's use Keynote. But if you're going to use Keynote, how do you get the words out of the presenter notes? Are you going to run that script? Again, with Reveal.js, it's easy, but Keynote isn't HTML. So how am I going to get those words out of this weird proprietary zip file format? Now, lucky for you, on macOS, the hooks used to script applications via AppleScript are actually exposed to Python. You can access them in a couple different ways, but there's a package called AppScript that makes it really easy. Let's take a brief interlude from the story, though, which does start to get a little complex, and get a baseline for something you can do with AppScript. Not everybody uses Keynote, but everybody uses a web browser. So, for our basis for comparison, let's grab the URL out of a browser window we have open. This is a handy piece of data to be able to capture. First, we'll open a browser window at a website I'm sure you're all visiting all the time, and then we'll write this quick script. We just ask the app Safari for the URL of the first tab of the first window, and presto, we can pull the URL out of it. But while this makes it for a good demo for showing we can get into an application and grab some data, we're not exactly leveraging the full power of Python here, so let's go a little bit deeper. Back to our hypothetical example of a talk at a Python conference. Rather than grabbing all the tabs from a browser, you can use AppScript to grab the first document from the Keynote application, loop over all of the slides, grabbing the presenter notes, and grabbing the words. But then, how do you know that these methods exist? What's like a Safari app or a Keynote app or a document or a slide? Well, every Mac comes with an app called Script Editor, which has an open application menu item that allows you to inspect the scripting dictionary of every application. Here, you can see a browser that shows what a Keynote slide is and where you can learn the name presenter notes. There's a simple system for translating from AppleScript syntax to AppScript's Python conventions, and once you've learned a few quirks, you can easily browse through whatever applications you've got installed to see if they're scriptable and what features they will present to you. But now that we've broken through the barrier to be able to program Keynote at all, maybe you can address one of the other big advantages of Reveal.js, which is syntax highlighting. In fact, it might have annoyed me. I mean, this is a talk about you giving a talk at a Python conference. The story is hypothetical. That Reveal's syntax highlighter doesn't quite work the same way as Pigment's, and so sometimes it's hard to get it to recognize new Python syntactic constructs like match statements or whatever. Plus, if the highlighter were in Python, you know Python, you could use fun features like everybody's favorite standard library module that you definitely already knew was in the standard library, ColorSys. That would allow you to add some fun flair to it, like the rainbow identifiers algorithm, which gives every identifier its own unique color to make it easier to pick them out and see which ones are the same on a slide. It's based on the deterministic hash of the string, so if it appears multiple times, you'll get that subtle visual similarity. But if something like capitalization differs, you'll see it stand out. This would be fun, right? And yeah, it's a little more challenging to implement. The whole program doesn't fit neatly on one slide anymore like the word count example does, but it's still pretty straightforward to create a new slide with a given code layout, populate it with some highlighted code that lives in a separate file so you can test it and maintain it in a Git repo and make sure nothing is broken. I do think this is a cool example, but it does immediately prompt the response, well, that seems pretty Mac specific. Is it just a sales pitch for Apple laptops? Well, kinda. I mean, I guess I do own some stock, but in the interest of fairness, let's talk about other platforms. macOS's scripting interfaces are unfortunately just a bit nicer than what's available on Windows and Linux in terms of exposing the internal model of scriptable applications in a legible way. And even if other platforms did have something similar, re-implementing that whole syntax highlighting hack for every different piece of presenting software would probably be too much time for this talk, but we can still get a lot done with the APIs those platforms do provide, so let's at least showcase reaching into the browser to grab the URL we're browsing on both of those. First, let's take a look at desktop Linux. The easiest option I found to drive Linux desktop apps is via accessibility. Not as many apps export a usable scripting interface on Linux, and we'll get to that in a second, but you may notice that the slide says import and not pip install. This package, PyATSPI, is already provided by your system Python installation, and for kind of boring reasons, it's a bit of a pain to get it set up to compile it, so you probably want a system site packages virtual env if you want to avoid that hassle. ATSPI arranges everything into a hierarchy, so we'll start off with a simple, generalized tree traversal function that can dig around through that hierarchy with a predicate. And once we have that helper, this is the whole script to grab the URL out of a Chromium window. We find the Chromium application, which is an object named Chromium with the role application. Within that application, we find an object named address and search bar. We pull out its text value with the getText method. And once again, we can run it and get the relevant text from the browser. But how do I find that stuff? How do I know the magic strings for Chromium and address and search bar? Similar to how there's an Explorer for scriptable interfaces on macOS, there's an Explorer for accessibility on Linux called Axerciser that can show you the hierarchy that the PyATSPI module exposes to you. You can dig around for the UI object you want to interact with, see what its name and role are, so you can find it programmatically. And fun fact, this tool is actually written in Python itself. Another way that you can control certain functionality on Linux is via a system called dbus, or the desktop bus. There are actually several options to control dbus from Python. I found DOSBus to be the easiest to use. Here's an example of how to resize a terminal window to the standard 80 by 25. There are actually two layers here. I'm using the GTK actions interface, which contains an activate method to activate the size2 action, which can separately be discovered by the actions list method. But once again, how did I learn all of that stuff? Once again, there's a tool that's native to the platform, a browser called dfeat, which does something similar to what Script Editor does or what Axerciser does for accessibility objects that can enumerate all of the dbus objects on your system. So we have two options for automating Linux and one for macOS. What about Windows? Well, we also have two options for Windows. Let's start with the easier one, which, as on Linux, is accessibility. You can inspect the accessibility hierarchy using the inspect.exe tool that comes with Visual Studio 2022's C++ profiling tools. Here I am using it to inspect the URL bar in an Edge browser window, which is viewing a website you can check out. On the Python side, there's a very capable library that can drive this interface called PyWinAuto. Using the information that I gleaned from inspecting that window, I was able to use PyWinAuto in just a few lines of code to grab the Microsoft Edge window from the desktop, descend down into the edit control, grab its value, and extract the URL, just as I did on Windows and Linux. Running it, you can see it print out the value that I would expect. As with many of these other projects, covering PyWinAuto in depth is an entire additional talk, but they have excellent documentation you can check out at your own convenience. Now, there is another way to integrate with scriptable applications on the Windows platform, which is the Microsoft Component Object Model, or COM, as is more often called, summarized by this amazing image from the Open Group's ActiveX Core technology reference from 1999. Now, technically speaking, it is the more structured option, gives more thorough access to certain kinds of internal functionality of applications that support it. So I feel like I should mention it. However, as you may note, the year that I am referencing for this technology was 1999. That may give you a flavor of the experience of trying to use it. In brief, it's not great. It does provide more structure and depth for those apps which do support it. Most don't. For example, notably, the Edge browser does not. And its use is kind of discouraged nowadays. But there are tools available to examine some stuff about its automation technologies, which are sometimes called COM or OLE, or sometimes if you search for VBA, you get it. And the way that you find stuff is you look in regedit to determine what keys are under HKLM software classes. Or there's also a tool that comes with PythonWin, also known as PyWin32, that allows you to browse the installed COM servers and find something about them. I'm not really sure what's going on there. Or there's this other tool called OLEview that can maybe present some more of this information in a more readable format. Unfortunately, most of the examples for deeper automation here are for Microsoft Office applications specifically. I'm mentioning COM because Office is a thing that a lot of people are going to want to automate, but I wasn't quite willing to buy the full Office 365 suite just for this one talk. So I was at least able to piece together, you can pass these OLE programmatic identifiers into win32com.client.gencache.ensure-dispatch, get an object with the methods that are described in the Visual Basic for Applications documentation that would allow you to script PowerPoint or Excel. And just to make sure I don't oversell how bad it all is, here's a quick example program that opens up the Windows shell, also known as the File Explorer, grabs its first open window, and prints out the URL to the folder it's viewing, even though I can't do that with Edge, and then resizes the window a little bit, making it 20 pixels taller, just to show that you can kind of script the application. Despite the fact that I don't have great specific guidance for getting started with comprehensive reference documentation generally, PyWin32 does have a nice feature, which is that unlike the other automation tools here, the built-in dir function will work on COM objects. This means that if you use something like the Python Win IDE bundled with PyWin32, it'll give you tab completion. You can just kind of fumble around the UI for whatever application you're using, tab completing various objects until you find something that looks promising. So, I've shown you ways to control other applications, but what if you want to write your own? Before we get into how, it's useful to ask why. We can get a lot done with command line tools and web pages, and even command line tools that we run locally, so what's the point of bothering with like a desktop UI? The first thing about desktop UIs is that they make it much easier to exert finer control over exactly what your computer will do when you push a particular key. Just for a really trivial example, this is an experience I have all the time with web apps. I head to a web page where I want to be typing into a text field, but some JavaScript misfires, or I click in the wrong spot, or I maybe hit tab or spacebar at an opportune moment, and then suddenly my keyboard focuses over here. I don't know how it got there, but the web page can't handle key events at all if my keyboard focuses over there, so my muscle memory doesn't work. It always seems like whenever I hit tab to try to get back to the relevant part of the web page, my browser decides I actually want to be navigating around through its Chrome, the browser bar controls, my bookmarks, opening up some extension, maybe tabbing through the links on the page. So I just have to click my mouse back on the part of the page I want to be interacting with. This isn't like a huge deal for filling out forms, but for UIs that I need to interact with like every day, where I want to hit a button and type a thing and hit a button and type a thing, it can get pretty annoying. A particularly intense form of the sort of control you might want to exert would be registering a global hotkey, actions that you might want to take while focused on any application, like starting or stopping a time tracking timer, opening up some quick reference documentation, locking your screen, or maybe something quite custom to your environment, like restarting a development service that's running in the background or reloading your code. Your command line or web-based application can't handle input if you haven't already brought them to the front. Related to those sorts of global actions, there's also the issue of persistence. It's all too easy to write a helper tool for yourself that you want to run in the background to manage something, and forget to start it up, or accidentally close it by hitting Control-C by accident. But if you just fork it off to the background, you have no way to interact with it once you close the terminal. Desktop OSs have an area for these sorts of minor background tasks. On Mac OS, it lives up in the menu bar. On Windows, it lives down in the system tray or taskbar, and it's handy to be able to put stuff there. Another bit of desktop UI that's helpful for these persistent background things are notifications. Every major desktop OS has a place to pop up little non-interrupting reminders of stuff that's happening, and it might be useful for your Python code to be able to produce those. Another thing that desktop apps can do that you can't really do from a web page or a CLI is a heads-up display that presents information continuously. I won't really have time to get into it in this talk, since this is the code to do this is a bit more involved and a little more platform specific, but my open source timer app, Pomodoro Boros, has some examples of drawing translucent UI over the desktop for macOS and a working prototype of a similar display for Linux. Finally, your desktop OS has a ton of capabilities that go beyond computation and UI. These are varied and inconsistently supported, depending on your platform. But one example is geolocation. macOS and Windows, and even Linux, have geolocation APIs. macOS has core location, Windows has the geolocation service, and Linux has GPSD and GeoClue. These can all be made available in Python by wrapping the native APIs and connecting to them. So hopefully that collection of benefits, more precise UI control, system tray UI elements in the background, notifications, varied display options like heads-up displays, and platform functionality like geolocation, has at least made you like a little bit interested in trying this out. But how do you do it? The first step is not to get too ambitious. It's easy to dive into the deep end here and overwhelm yourself with complexity. So first, figure out which bit of functionality you're really going for. If what you need is just a couple of native-looking UI elements, the standard library's got you covered. TK-Inter's gotten a little bit of a bad rap over the years. For many years, it was like super ugly and honestly kind of broken on a lot of platforms. And it still probably wouldn't be my first choice for like a high-stakes desktop experience. But the core Python team, not to mention the TickleTK team, has been quietly improving in the background for years. And for a lot of basic use cases, it's actually pretty great. It's also cross-platform, and on any of the big three platforms, it pretty much works right out of the box nowadays. So this tiny little program, cribbed from the standard library's docs, is all you need to get started. This was definitely the quickest demo I had to cook up for this entire talk. But you might look at this window and think, that's not super ugly or anything, but the padding is kind of off and it doesn't look very polished. And sure, it takes a little bit of work if you want it to look good, but if you haven't taken a look at Idle, Python's built-in TK-Inter based IDE, You might be surprised at how pleasant and polished it looks in 2025. You can really get a lot of mileage out of this extremely simple, cross-platform, beginner-friendly, thoroughly well-documented, integrated tool. However, it does still have some issues. Although the TK dev team has finally picked up some work on this in 2025, TK still doesn't provide accessibility access, so blind users can't use anything you make with it. And the TK libraries add some quirky constraints to the packaging requirements, which makes it pretty annoying to bundle up anything that you've made with it for other folks who don't have Python. So it's best for environments where you need to whip out something quick for yourself or some other users who have Python, but who might not be able to pip install anything. Luckily, there are even better options just to pip install away. In particular, Beware's cross-platform toolkit of Toga and its build system of Briefcase can get you started in a similarly small amount of code in a way which provides accessibility and a streamlined build pipeline. Hello World application is almost as small as in Tkinter. Again, fits comfortably on one slide. I timed myself getting this demo up and running, which I did about 25 minutes ago. Including modifying the code to add the button, it literally took me 115 seconds start to finish. So, and I don't know Toga, so this is very easy to get started with. For that even finer grained control I spoke about earlier, I released a library for the Mac called Quick Mac Hotkey, which is a single platform tool, but it's pretty easy to use. Once again, the fully functional single slide demo looks like this. This globally captures the Command-Control-J shortcut until the user presses it, then unregisters it. This whole library is basically just this one decorator, and it integrates with any application using an AppKit main loop. Here, we just run it using PyObjective-C. There are also portable options if you want something that runs cross-platform. It takes a bit more than a slide's worth of code to get the PyPI package global-hotkeys going, but it will let you grab hotkeys on every platform. I also wrote a similarly tiny library called Quick Mac App, which I am using in a few applications. It makes a status item and runs a twisted main loop for you, so you can easily run whatever networking code or event handling code you need to. Again, one slide example, just decorate your function with the main point decorator, set up your status menu by instantiating a status class and calling the menu method on it with some items and the callbacks you want them to run. And squeezed in among those status items, you can see your status item. Next, if you want to pop up a notification, it's so simple you don't even need to write any Python code. You just pip install Notify Pi and run its command line tool, which works on macOS, on Windows, on Linux, all using the native notification centers for each platform. And of course, it is a library, and so if you want to write some Python code with it, you can. It's really quick to create a notification and populate it with whatever information that you need in the background. Okay, next up, let's determine our geographic location with these fancy platform APIs. For Windows, we can install the WinSDK package, which is a community-supported fork of Microsoft's lightly maintained WinRT API bindings for Python. And on macOS, we can install PyObjective-C framework core location, which wraps the built-in core location framework. We could also pip install PyObjective-C, but that will drag in a lot of extra libraries we don't need. This here is some code to request the location from macOS. Once again, as with AppScript, there's a translation layer you need to learn about here. PyObjective-C has a bit of documentation to get you started, but core location is just documented on the Apple developer site. It is not a Python thing. The main thing here is that we implement this location manager underscore did update locations underscore method, which is documented in the Apple core location documentation as location manager colon did update locations colon. You don't need to learn Objective-C all the way in order to be able to read these APIs. You just need to do a little regex substitution in your head where you can see a method signature like this and translate it in your head to a Python method signature like this. Similarly, we use the Windows API that does a similar thing. Here we're using the geolocator object that we're calling getGeoPositionAsync. And we are awaiting it because WinRT actually integrates nicely with Python's own async IO. We look at the Microsoft developer site to look at the Windows platform API for doing the same thing. And it is getGeoPositionAsync with capital letters. And so we need to do another mental substitution. This is a C#, which I don't even know a little bit, but I can easily replace those intercaps with some underscores, add an async, and once we know the Python signature, it's easy enough to just call. So, okay, that was a lot of code. Let's summarize. Broadly, there are two ways you can make your desktop or laptop computer do some cool tricks. One, you can use a cross-platform library. I gave a tour of tkinter and NotifyPy earlier in this talk, but there are plenty of others like Toga, PyQt5, PyQt6, WXPython, Kivy, and these libraries can wrap a ton of functionality, and they typically have full documentation in Python. You rarely need to learn all that much in the way of a new skill, just a new API. But if you need the full unredacted raw power of your whole platform, even that isn't too hard. Your operating system's native APIs do have a bit more power, but you need to learn to translate from the system's native language into Python in order to leverage the automatic wrappers that have already been written. The documentation for these platforms is extremely extensive, and if you want to learn how to do something that you've seen another app do, the information is definitely possible to find without leaving one of these main documentation sites. So I wanted to give this talk for a couple of reasons. First, I've got some ulterior motives. I use these tools. I try to automate my computer pretty regularly. I'm working on a few desktop apps, and by far the most painful part of this process is dealing with documentation that is out of date or incomplete. As you've seen, actually using these libraries is fine. The code fits on a slide. Not a lot of tedious boilerplate, but figuring out how to get started, or even if what I want is possible, can have some pretty high static friction just to get going. For one thing, in order to bubble up the good current documentation to the top, search engines need to have new content where people are linking to good resources, fresh blog posts that actually document the state of the art. Even if a library is actively maintained and still works great, if every blog post is from 2009 and has a Python 2.6 syntax in it, it can be quite tedious to figure out how to make it work on a modern system. Maintainers also need the sense that people are actually using their stuff. When new people show up and ask questions, it makes the effort of maintaining the project feel more meaningful. For one quick example, and I don't want to throw any shade at other maintainers here, I just want to point out that one reason I chose DasBus rather than the official Python dbus is that its documentation includes a couple of revealing issues. To be clear, it's not that DasBus has replaced it. The Python dbus is software people use every day. It's included in Linux distributions. Tools in the distributions themselves rely on it. But it still documents certain things on its read the docs page like this. The unique instance idiom is important enough for a whole section of the docs, but the section reads, "Fix me, provide exemplary code, put in examples." It leaves me wondering what it is, and do I really need to know about it? So that's it for me and my purely selfish motivation. But there's a second reason that I wanted to give this talk, and that's what I hope I can give to you, the audience. The software industry's reputation is somewhat deservedly tarnished over the last few years, and in the noise about the struggles of the titans of tech, we can lose track of these small, personal, joyful experiences that tech can produce. But we can artificially limit our thinking about possibilities based on economic pressures, day-to-day concerns, and just what we're used to. We kind of put barriers in our own minds around what's possible with our computers. So let me tell you a story about the very start of my software development career, if you could call it that, the first time I experienced one of those barriers. I did not start programming in Python. I started programming in HyperCard in the early 90s. I didn't particularly want to be a programmer. I wanted to be a writer. But as an 11-year-old, I was a big fan of choose-your-own-adventure books, and the possibilities of interactivity intrigued me. One of the most famous success stories for HyperCard was the 1993 breakout hit video game Myst. It used the simple tools I was already using, card transitions, background images, and custom cursors to produce the feeling of being really immersed in an imaginary world. Of course, one big difference between my work and theirs was the use of color. Attempting to do it in monochrome obviously wouldn't feel the same. The problem is, while HyperCard had a super friendly authoring interface that was appealing to a kid who didn't really want to be a programmer, looks like I messed that up, HyperCard did not natively support color and required a binary extension called an X command in a different programming language. This was real programming, the sort of thing I found intimidating. Even installing the X command for color, if I knew where to get it, which I didn't, required skills I didn't have. Attempting to do this required leaving this, the comfortable, cozy, easy world of HyperCard authoring, to this, the world of ResEdit and compilers, the Macintosh Programmers Workshop, and a bunch of other tools that were immediately baffling to me in their complexity, if they were even available at all. Most of them cost a lot of money at the time, and you had to go out to a store and get them on floppy disks. There was a wall between the easy-to-use learning environment of HyperCard and the real programming tools that let users make real applications that look professional and polished. So I gave up. As a teenager at the dawn of the internet and no credit card, this was an insurmountable hurdle. And if I couldn't get those tools, And if I had gotten them, I wouldn't have known what to do with them. It was a decade before I tried again. But with Python, we don't need to have this problem. The barrier between the stuff that you can learn in a tutorial and the full power of your personal computing universe is just an import statement, or more realistically, a pip install away. Almost all these things are free, documented, ready for you to use right now. Not only is the Python stuff free, not only are the Python libraries open source, but all of the developer tools for the major platforms are also relatively easy to download these days. Even Visual Studio, the community edition, does everything that you need. You don't need to learn a different programming language or give up the library ecosystem that you already have. If you want a desktop app that does something that Python can do really well already, that you already know how to do with Python, you can just do it. So that's been it for me. Go out there and program your computers, and I think we might have time for one question. All right. Thank you very much for your time.
I'll ask something. That library you mentioned at the beginning, AppScript, its website sort of, you probably know this, says we don't really recommend it anymore. We're not sure what's going on with AppleScript. Is it your experience that that's fine and it's still great, or at least great for personal stuff? Or
that comment, along with many other comments about how AppleScript is unmaintained and Apple's going to kill it in the next OS release, is from, I think, 2012.
Okay.
So I feel like we're doing all right.
Okay, fantastic. And it's
kind of, it is unmaintained, but or rather, it's very lightly maintained. It's the author HHAS has released new versions whenever new OSs come out or build configuration changes need to be made, but the library itself is kind of done. AppleScript has a long backward compatibility history that just needs to be maintained forever, and so the tool just kind of does what it needs to do. I have had zero issues with it over many years of usage. And I did kind of worry the first time that like the binary wheel was broken, but it got fixed within a couple of weeks. So, yeah.
Okay, and so they put out new releases for new Python versions and everything has been fine.
Yeah.
Fantastic, Thank you.
All right, well, I think that's it for me then. Thank you very much, everybody.